Welcome back, everybody, and apologies for the construction work which is going on close to our lecture hall, which means that we have relegated ourselves to a fully Zoom session. Now, what I wanted to say is a little bit about the plans for the rest of the semester. So we can have at most 2 more lectures after this one. So the aim today is to give you a kind of summary of variational autoencoders, and then we're going to move on to a discussion of generative adversarial networks, or so-called GANs. And after that, we will start briefly a discussion of diffusion model, which is going to be our last topic. Now, there are quite some good reading recommendations, although this is a field which changes or moves swiftly, which means that many of the things which you see in the textbook by Goodfellow et al., although they describe the methods which were presented then, some of these methods are now less popular, like we discussed earlier about restricted Boltzmann machines, whereas diffusion models, which are normally not described in many textbooks, are gradually now taking over, especially when it comes to image generations, movie generations, or making music or whatever. So the aim today is to cover roughly 1 and 2, and we are going to have a quick reminder on with a summary of autoencoders, and also a little bit about Boltzmann machine, just to remind you of that. And one of the topics which we ended up with when we were optimizing the probability distribution is something which we call contrastive optimization. So I wanted to just take some time and remind you of some of these basic concepts, and then summarize our discussion of variational autoencoders before we move over to GANs. Now, the one thing which can be useful to do then is actually to remind ourselves about the general picture. So what I'm going to do now is just to switch to my whiteboard. So let's do that. So if we think of the basics of so-called generative models, so what we have is this kind of general container of generative models or methods. And if we box it in here, we have essentially 2 types of approaches. One, where we deal explicitly with a probability distribution. PDF. And then we have the implicit PDF. So PDF stands for a probability distribution function. And when it comes to the implicit methods, what we have is generative adversarial networks as one of the methods. And then there's a method which we haven't discussed much, and that is simply called Markov chain sampling. And that has become not that popular. So generative adversarial networks are those which are commonly used. Now, when we now look at the explicit treatment of the probability distribution, one of the things which we end up with then is a set of methods which we would label as approximative. So we do an approximation to the probability distribution, but we still treat it in an explicit way. And among the approximative methods, we discussed restricted Boltzmann machines, or RBMs. And in the previous 2 weeks, we also went through the mathematics of variational autoencoders. So these would be methods which now treat the probability distribution in an approximative way. Then there is something which is more labeled as tractable, and we haven't discussed that either. But that belongs to the type of methods which are often called belief networks, so fully visible belief nets. So I'm going to write that out here, fully visible. And we have not covered that topic either. And nowadays, we can actually add diffusion model to the approximative ones. So we should add here diffusion models, but they are a little bit different. But let's see if we now want to mark out what we have covered or are going to cover fully. We have been discussing restricted Boltzmann machines, variational autoencoders, and we're going to discuss diffusion models. So Markov chains is something which we have scratched the surface of, but we will not spend time on that in this course. And then also fully visible belief nets is something which we haven't discussed. And then we have all the family of discriminative methods, which we discussed earlier and which you have been exposed to in previous courses as well. Now, just to remind ourselves briefly of what this thing is about, if we now look back a little bit at what we started with, so we have a probability distribution, p theta of x, which normally is called the marginal distribution, and this is a quantity which we want. And we train that against data. So we want this quantity. And in general, this quantity is now given in terms of an integral or summation if these are discrete events, where we have a domain of so-called latent variables. One way to view that is just as you having additional degrees of freedom, like when you set up a neural network with hidden layers. So H could be the hidden layers in a Boltzmann machine, or it could be the latent space in an autoencoder, or it could be the latent space in a variational autoencoder. So many of these methods, they are based on playing around with the chain rule for probabilities. So we would typically write this. So theta is the set of parameters which we have. And this is the probability of x and h. And this gives the marginal probability because at the end, we are looking at some input data x as a function of a set of parameters. Probability. In general, this function here is then rewritten. This the probability is then written by the chain rule of probabilities as the probability of x given h, and then multiplied with the probability depending on this parameter of h. So this is, as you can see here, when we are doing this kind of calculations, we have two kinds of criteria which we would like to bake in. So I'm mentioning this because this motivates the introduction of diffusion models later. So we want these probabilities to be tractable. So there's a question of tractability, which means that in general, since this probability is a multidimensional function, it can be difficult to actually handle this probability. So tractability means often that we have a simpler probability. So the PDF could then be Gaussian. It could be an exponential probability, it could be a Laplace probability, etc. Many of the standard probabilities. This has the feature that it can often easily be used to fit data sets. However, it has less flexibility. So we actually want both tractability and flexibility. So flexibility is actually the feature which allows us to adapt a probability distribution to complex data structures. Now, in general, as you have seen from the discussions previously, to find this quantity here essentially means that we would have a model, or somebody has given us this probability distribution, the likelihood of finding x given h, and then we would also have to know the probability of finding h, which is again the marginal probability for that specific quantity. So in a certain sense, this sounds like an impossible mission, especially if you look at the requirement on flexibility, because in general, as we said, this probability distribution is a highly dimensional probability distribution. Now, one of the theorems which play a very important role is actually Bayes' theorem. And let us quickly remind of ourselves about some of these other probability distributions. So we can actually, if you look at this equation which we have here, we can rewrite that same probability distribution, p theta of x of h in terms of p theta, and then we have h given x, and multiplied with p theta of x. Which means that we can now, as you can see here, we can define a probability of finding h given x multiplied with the probability of having x. And these two quantities which you see here, they combine to give what's normally called Bayes' theorem. Now, when we are looking at autoencoders, one of the things which we, and variational autoencoders in particular, what we end up doing then is the following. So we would have, if we now remind ourselves about the variational autoencoders, so we would have our data set here. And let's label this as D. And that is fed in, so this is a domain of data set of X. And we just call this for the X space. This is where we have the events. Now, what we are doing then when we are setting up a variational autoencoder, which is not exactly the same as a standard autoencoder, is that we encode the information. So this is called the encoder. And this is now given by, in principle, it should be given by the probability of having h given x. This is the ideal. However, we don't know this function, so we have to make a model for it. So that probability is now replaced, since we don't know it, with a new probability, which we last week called for q of phi, so where we have own parameters for that. And this is given by h with a given x as input. So what we are doing now is to take the original x data which we have and then encode them through this function. And this function gives us now the probability of finding h. This quantity is then sent over to a latent space. And in this latent space, what we have now is a set of variables h, and they have a probability which we call the prior, a p theta of h. And this is a function which is then reused as input to the decoder. And that function there produces now the final probability, which we call for p theta of x given h. And just to remind you that the final quantity which we want, p theta of x, is now given as this integral over d of h element in a given number of variables d, and multiply with p theta of x of h and p theta of h. So this is the quantity which we end up with when we have run this information from the latent space through the decoder. Now, what you see here is that we need models for this quantity here. We would also need models for this quantity here. And similarly, we also need models for this quantity here. So if we go back to that argument here about tractability and flexibility, you see quickly that what we are doing now is that we are trying to deal with the full probability, but we approximate the full probability. And this is why when we now look at the general scheme of generative models, that the variational autoencoder is actually an approximation to an explicit treatment of the full probability distribution function. So if we look at this kind of, or take this kind of overarching view on things, then what I wanted to do now is quickly to revisit some of the basic ingredients which allow us to actually perform these calculations. Because when you look at the scheme here, this sounds almost like an impossible calculation. And one of the things which we want often is that this latent space is actually much smaller, or in general smaller, than the original space X. If you think back to the traditional autoencoder, what we had there as well was an encoder function, which could be a standard feed-forward neural network. And we use that one to project down the information to a smaller space, a latent space H, which we then fed into through a new function, which could be a neural network, to a decoder. And that decoder was meant then to produce an output, which we label as an X tilde, which is as close as possible to the original value X. So this kind of procedure is the one which we use in order to optimize the probability distributions based on a given data set. And when you have such a probability distribution, that is when you can start generating new data. Because at the end, the desired product which we want is this probability distribution, which has been trained on some data, but we can use this probability distribution to generate new data, because at the end, what we want, if we just put this aside here, is to generate new X based on the probability distribution which we have obtained by training on the data. Now, as we discussed last time, when you look at project number 2, for those of you who want to do that, we would normally recommend to deal with restricted Boltzmann machines, because this is something which, if you're coding this from scratch, this is something which can be done within the span of 1 to 2 months. To encode a variational autoencoder, we would normally recommend, if you want to write your own code, there are code examples in the lecture notes from last week and the week before, where we use PyTorch to encode a variational autoencoder. But in general, if you want to write a variational autoencoder from scratch, this is something which can be pretty laborious, and it would take roughly more than 1 to 2 months. This applies also to the case of GANs, if you want to write your own generative adversarial network from scratch. But we do have examples, which we will cover today, written in PyTorch for a more simpler example of a generative adversarial network. So what I'm going to do now is to go back a little bit to the slides and remind you quickly about the discussions which we've had about the variational autoencoders, but also Boltzmann machines, so that you can see the wood for the trees. So let's go back to the Jupyter notebook. And please feel free to ask questions. So when you now look at the machinery which we started with, the basic operations, so we have a probability for a given set of stochastic variables, which is simply given by the product of all the individual ones. And this is why when we want to optimize this probability with respect to some parameters, we normally take the log of this probability and we assume that these are independent and identically distributed events. So one of the problems which you see immediately when we want to deal explicitly with the probability is that we have a normalization factor, where we borrow the terminology from physics and we call it a partition function, which is in general intractable. And we saw that when we discussed the restricted Boltzmann machines, that even with some few degrees of freedom, the number of possible combinations of X and H, they quickly exceeded what was feasible to deal with. So the quantity which we want at the end is the one which you see here. And since this is going to be given by the product of all these quantities, so this is the typical quantity which we end up with, which we want to optimize. And when we plug in the probability distribution properly with the normalization constant, this is the quantity which we want to calculate. And we went through this 4 weeks ago, so I'm going to just quickly remind you of this, because that shows you essentially the kind of problem which we end up with. So if we look at this equation here, we end up with a maximization of this probability distribution, and we would typically take the log. Alternatively, we can minimize, and that means that we take minus the log, and then we minimize the problem and find the optimal parameters. So this is a straightforward approach which has been used in calculations of restricted Boltzmann machines. For the variational autoencoders, we actually encode the information through a new probability distribution, which has a set of parameters phi instead of the global parameters theta, which you have here. And what we want is obviously that the gradient is equal to 0. And the quantities which we end up dealing with is actually the calculation of two expectation values. So let me just bring this up, the final equations here, after all this algebra, because we went through this before. So we can actually calculate the derivative of the partition function as a function of the parameters in terms of an expectation value. So this quantity which you see here, this one, is now replaced by an expectation value. And we are going to generate these with a model for the data in order to calculate the expectation value. So we need to have a model for this function f. So this is calculated with respect to the probability distribution which we have defined. And this quantity here is then calculated based on the data which we have. This is called a contrastive optimization because we have a quantity with a positive phase and a negative phase, and it's the balance between the two which leads to the optimization problem. Now, you can change the sign and take minus log, and that means that these two quantities will just change the sign. That doesn't change the picture when it comes to the optimization part. Now, when we went over to variational autoencoders, we actually start with the same equation, but we used Bayes' theorem to rewrite some of these quantities. And then with Bayes' theorem, we could then introduce this approximative probability, which we call Q. And then we use also what was called the Kullback-Leibler divergence in order to set up the expressions or a calculation of recipe, and in order to be able to set up the algorithm. So variational autoencoders are used quite a lot. They can be somewhat difficult in training because we are still dealing with the models for the probability distributions, and somewhere we have to replace the explicit probability distribution with some kind of model, especially for the latent space. So there is a link in the lecture notes, which I invite you to take a look at. And this is a set of notes on the optimization where you replace this function f here. Instead of having a model like we had for a restricted Boltzmann machine, you can replace this one with a feed-forward neural network, or you can replace it with a convolutional neural network. And if we take a closer look at these slides here, you will now see a general layout. And in this case, the author is using TensorFlow in order to set up the energy-based generative models. So when we looked at Boltzmann machines, we would call this function f, which we have here, for an energy function, which is inspired by the usage of the Boltzmann distribution, and that's why they're called Boltzmann distribution. But you're not limited to these kind of models, but you can actually replace that with a standard neural network. And if you scroll down here, you will find examples, and one of these examples is actually taken from the textbook by Foster, which we have linked in the beginning. And you can see again that this is the model for the probability distribution which we are setting up. And instead of having this as given by, let's say, a simple model inspired by statistical mechanics, statistical physics, you would replace this one with a standard neural network. And there is a discussion here on the contrastive divergence and how you would typically train these models here. And I invite you to take a closer look at these discussions here. But in general, what we are doing now is to replace the exact probability with some probability Q or phi here. Now, this quantity, the first one, as we have in the notes here, is calculated with the data which we have. Whereas this quantity here, this expectation value, which we have down in the notes here, this quantity here is now calculated with your model for the probability distribution. So in a certain sense, if you want to take a kind of view on these probability distributions, a generative model takes some input and produces some output, and then you want this probability distribution which is generated to be as close as possible as to the realistic probability distribution, or the ideal one which describes your data. So let's quickly remind ourselves about the variational autoencoders, which we looked at last week, and then try to wrap up that discussion. And I invite you to take a look at the codes which we discussed in week 14. So essentially, and what I've done now is to suppress the dependence on this optimization parameter theta. So in principle, what we have is a probability x of theta, which is the marginal probability. But here in the equations, just for the sake of simplicity, I've just skipped this theta dependence, which you see here. So this is again the same equation which we discussed before. And when we now look at the chain rule of probability, this is something which we can rewrite. So this P of X can be rewritten like this, or alternatively, it can be rewritten in terms of P of H as a function of X given H multiplied with the probability P of X. So directly computing and maximizing the likelihood, as we said, is difficult because it involves either integrating out all the latent variables, which basically is intractable for complex models, or it involves having access to a ground truth latent encoder. So when we look at that scheme, which we discussed earlier, this latent encoder here is something which we need to make a model for. So if you look at the last two equations here, these were the two equations which we used last week to derive what is called the evidence lower bound, or ELBO, which is, as the name suggests, a lower bound of the evidence. The evidence is then quantified as the log likelihood of the observed data. And this is the quantity which we then optimize. So formally what we did last time was actually to then produce this expectation value of the log of the probability distribution. So we are replacing this PH of X here. We are replacing that one with a model which we called Q of phi. And this is this model Q phi here. So the equation which you see here, this one for the probability distribution using the chain rule of probability, gives us then something which we can rewrite in terms of this expectation value here, but where this distribution is the one now which is the relevant one. So this is the quantity, this is actually what you see here, is nothing but a rewrite of P of X. So mathematically, what we showed last time is also that the log P of X is larger or equal to this expectation value, because we can rewrite using the Kullback-Leibler divergence. We can actually rewrite this equation here in terms of this equation plus the Kullback-Leibler divergence, which is always positive. So the encoder function is a flexible approximative variational distribution with some parameters phi that we're also trying to optimize. So we would have the parameters for the encoder, which then transfers us from the input data to the latent space. The latent space is assumed to be much smaller in dimensionality than the full space of the input variables X. And then we define a prior probability, the probability of H. And then from that one, we can go back and reconstruct the probability P of X given H. And then we can integrate up and find the final probability P of X. So from last week, one of the things we did was when we looked at this log P of X, we simply took and multiplied this one by 1, because we're assuming that this probability is normalized. And then we can then, since this is the integral here, actually this should be an integral over H. This is not Z, it should be H. This is a typo from my side. Let me just note that one. Okay, so this is an integral of H here. And our quantity, which we are calculating the expectation value of now, when you look at this quantity, because P of X does not depend on h here. So we can then put that in here as a log. And that means that the function we are calculating is actually the expectation value of log p of x, which we then rewrite in terms of the product rule for probabilities, which is just this one. So everything we did last week was just a manipulation of some of the basic equations in probability calculus. And then we simply multiply by 1 again, and then we can rewrite this equation in terms of two expectation values, all defined in terms of this function q here. So we split the expectation value, so we have this q, and the interesting thing now is that this quantity which you see here is nothing but the quantity which we defined last week as a Kullback-Leibler divergence. And that quantity here is a positive quantity, it's equal to 0, and it's equal to 0 when the model which we make for this probability or this likelihood is equal to 1, because then we have log 1. So when these two probabilities are the same, then we just have log 1. So these are just, manipulations of the expression for the probability we want to find, where I have now, keep in mind, I have suppressed the parameters theta. So when we are doing the optimization, it means that we are doing an optimization with a parameter, with respect to the parameters theta, but also with respect to the parameters phi. And since this quantity here is larger or equal to 0, then we end up with an expression here for this quantity, which is the one we want to optimize at the end, which is always larger or equal than 0. So from this derivation, we observe that the last equation, that is evidence as we call it, is equal to this estimated lower bound plus the KL divergence. So the evidence which we want is actually this probability distribution. So we can rewrite it in terms of models here. And then we have a relation between the approximate posterior and what we call the true posterior. And understanding this term is actually key to understanding not only the relationship between the estimated lower bound and the probability we want, but also the reason why optimizing this is an appropriate objective at all. So optimizing this function here, that means taking the derivative of these functions, is the central ingredient in the variational autoencoder. So to bring up the image which we had on the slides, so let me just bring those up here. So after all these manipulations with the chain rule, marginal probabilities, conditional probabilities, and Bayes' theorem, what we want then is when we take the derivative of the probability distribution, that quantity with respect to the parameters, we have broken this one down into an approximation to this so-called posterior, which encodes the data and then allows us to perform a dimensionality reduction to a smaller space, a latent space. So the hope then is that we don't need that many degrees of freedom here. If you're thinking back in terms of a Boltzmann machine, what you could think of is that in the Boltzmann machine, we don't have the encoder part, but we do have the hidden layers. So you could now think of you having an image which you feed into a Boltzmann machine, and this image could be given by, let's say, 100 times 100 pixels, which means that you would have 10,000 pixels for each image. But then your latent space could just contain some few hidden nodes. So that means that there is, also when you run with a Boltzmann machine, there is a considerable reduction when you go from the input to the latent space. Here, we are now using Bayes' theorem combined with the chain rule for probabilities in order to approximate the likelihood for going from X to this latent space, and that is given by this encoder function. And as you will see now, this kind of encoder probability is often given by some known probabilities. That brings us back to this problem of extractabilities and flexibilities. So the flexibility is something we want to have in order to deal with complex data sets where we may not be able to describe the data in terms of some simple probability distribution like a Gaussian. So tractability, on the other hand, means that at the end, we actually want to be able to run some calculations, and then we need to plug in a model. So the Kullback-Leibler divergence gives us then also a measure of whether this probability here and these probabilities match each other. So let's go back to the slides and take a closer look at some practicalities, which we left a little bit open last week. So from this derivation, as you can see, we have now we need actually to define a function for this posterior probability. So in the default formulation by Kingman and Welling, and last week we set up also a link to their tutorial about the variational autoencoders. They directly maximize actually this quantity, and this approach is normally called variational because we optimize for the best probability distribution amongst a family of potential posterior distributions, which are then parameterized by phi. So this is what we call the autoencoder, or just the encoder. And when you look at these equations, this quantity which we are looking at here, when we rewrite it, so we can split this expectation value in terms of this quantity here, which is now an expectation value of this probability, which we need to find the final probability. So again, you see here, we're just manipulating with the chain rules of probabilities. So we can calculate this expectation value based on this approximate model. And finally, we have this equation here, where we have the probability or the prior for the latent space, and then multiplied or divided by this quantity here. And this is nothing, again, but a Kullback-Leibler divergence, where we simply have inverted these two. And then we have this term here, which is normally called the reconstruction term, because at the end, this is the quantity which we want now in the decoder. So the decoder part needs this term here. And the calculations here, then when you look at these explicit expressions, what we do now is that we learn an intermediate, and this is often called a bottlenecking distribution, that can be treated as an encoder. And it transforms input in distribution of a possible latent, the latent space. And simultaneously, you learn a deterministic function, P of X given H, to convert a given latent vector H into an observation X, which then can be treated as a decoder. So the decoder part is given by this function here. So as you see, what we are doing, and sorry for repeating myself, we are just manipulating different expressions for the final probabilities in terms of Bayes theorems, posteriors, likelihoods, prior probabilities, the chain rule of probabilities, and marginal probabilities. So the decoder and the encoder, so the last two terms in these equations, so this equation here, they have intuitive description. The first term measures the reconstruction likelihood of the decoder from our variational distribution. And that ensures that the learned distribution is modeling effective latents that the original data can be regenerated from. And the second term measures how similar the learned variational distribution is to a prior belief held over the latent variables. And minimizing these terms encourages the encoder to actually learn a distribution rather than collapse into a Dirac delta function, which is what would happen if you didn't train here. So maximizing this elbow, as we discussed, is equivalent to maximizing its first term and minimizing its second term. So what happens then, we need to set in some actual terms. And one of the defining features of a variational encoder is actually how this estimated, or the lower bound is optimized over the parameters phi and theta. And the encoder, the variational autoencoder, is commonly chosen to model a multivariate Gaussian with a diagonal covariance. This is the most common choice. And the prior is often selected to be a standard multivariate Gaussian in terms of these latent variables with zero mean and just a variance which is equal to 1. And then the kind of equations we end up in is actually to optimize. So we would optimize with respect to phi and theta, this quantity here, and then we have the Kullback-Leibler divergence. And at the end, what we do now is simply to sum over all these observations here, where this latent H is sampled from this Q of H given X here, for every observation X which we have in the data set. Now, one of the problems, and this is a technicality, and is called the reparametrization trick, is that each of these H that we need to compute is normally generated by a stochastic sampling procedure, which is generally not differentiable. And this is normally addressed by what is called the reparametrization trick, where this function, this posterior probability, is designed to model certain distributions, including the multivariate Gaussian. And the standard trick is actually to reparametrize a random variable as a deterministic function of a noise variable. And this allows for the optimization of the non-stochastic terms through gradient descent. And I invite you to take a look at these details because these are the kind of technicalities which are needed when you're training a variational autoencoder. So after training the variational autoencoder, generating new data can be performed by sampling directly from the latent space. So you have this probability P, which you made a model of, and then running it through the decoder. And the variational autoencoders are particularly interesting where the dimensionality of H is less than that of the input X. Because then we have something which is actually tractable. So this concludes the discussions of the variational autoencoders. In the slides from last week, there is also a code example written in PyTorch, and I just invite you to take a look at that code example. So we're going to take a small break, and after the break, we are going to look at the generative adversarial networks. Welcome back after a small break. So the aim here is to give you a brief overview and introduction of generative adversarial networks. And this is something which has, as you can see from the slides here, it has quite an interesting background story. So GANs began, according to legend, as a discussion argument in a bar where Ian Goodfellow, one of the authors of the textbook on deep learning, they were actually discussing work related to generating data using neural networks. And after all these discussions, Goodfellow actually went back home and during the evening coded a generative adversarial network in terms of two standard neural networks which were competing with each other. So a generator network is composed actually of two parts, and you can think of these again in terms of autoencoders, like an encoder part and an decoder part. And they are implicit density functions that sample directly from some underlying distribution. And they do this by defining a two-player game of adversaries. And the adversaries compete against each other under well-defined reward functions. And each player, in a sense, tries to maximize its rewards. So let's now look a little bit at how we can think of such a network here. And these networks are extremely popular and they're widely used. And the fact that you sample from an underlying distribution and that you're implicitly defining a density function gives them much more flexibility than what we saw with variational autoencoders or even restricted Boltzmann machines, which are much more limited in a sense. Although the energy-based models have seen a revival in the last years due to us replacing the energy-based model with say, a neural network. But GANs are extremely popular and they are widely used for image generation, text-to-image analysis, face aging, image-to-image translation, video synthesis, and much, much more. Now, in the textbooks which we have linked with the course, the textbook by Foster or Babok and Bali, and also the textbook by Rushka, there are several examples on the setup of these different type of networks. So we are going to look at a simpler case, and I have borrowed several figures from the textbook by Rushka. So the kind of idea is that you have a generator or an encoder which takes in some data. In the beginning, these data are normally generated by, let's say, uniform distribution. So you're basically producing some noise. And then these are fed into a discriminator, which also receives information from the real image or real data. And this discriminator tries to figure out whether this is a real representation of the data or whether it's a fake. So if we want to dive a little bit deeper, let's now just jump into the Jupyter notebook here. The whiteboard. So we can think of this in terms of two generators or two models. So there is the discriminator model. And this discriminator is actually a differentiable function that tries to maximize a probability of 1 for samples which are drawn from a training distribution. So this is in principle a differentiable function. So we are trying to maximize the probability T of 1 for samples which are drawn from some training distribution. It's given by a training distribution. So the simplest case is actually two kinds of neural networks which are set up against each other. So you could now think of, if we want to make a sketch here, so we have some input sample. And this is our training data set. We feed this into some kind of differentiable function. So one of the things which is important in basically all these trainings of probability distributions is that these functions are differentiable, because then else it gets very difficult to actually perform the optimization. So there is some differentiable function, which we just call for D. And we want this to maximize a probability. The probability of this D of X, and we want that one to be equal to 1. So this would be the basic layout, more overarching view of the discriminator model. So this is the discriminator model. And the discriminator is also used to classify whether the output from the generator, so there's a generator as well, so it's actually two neural networks in the simplest case, and this is the way it was laid out by Goodfellow in the first approximation. The generator can also feed input to the discriminator, and then the discriminator needs to decide whether the data which are produced by the generator are real or fake. And the main utility of this model is actually to help to develop a generator which is robust. And when it's used, when this discriminator is used to classify output from the generator, then we would label that as a D of G of H, where H is now the latent space again. And this G of H is the output from the generator model. If we now look at the generator model itself, this is actually what we would call the primary model of the whole competition between this discriminator and the generator. So you can think of this as a kind of game. And this model generates samples that that model generates samples that are intended to resemble the samples from the training set. So let's now define, so this was a discriminator. Let's now move on and define the generator. So this is, as I said, this model generates samples. So generate samples which are intended to actually resemble those from the training set, that are intended, that are meant to resemble those from the training set. So the model takes normally random unstructured nodes as a kind of input. You could typically have a uniform distribution, which is defined by the degrees of freedom of a latent space. And then it tries to create a varied set of outputs. And the generator model is also a differentiable function. In general, we want it to be a differentiable function because else it's almost impossible to calculate the derivatives of the cost function, which we're going to optimize. And it is often represented by a deep neural network, but it's not restricted to that. And you will also see that if you go into the textbooks, which we have listed in this course, you will see examples of people using convolutional neural networks or more complicated networks than just a deep neural network. So if we call this generator for G, you could then make a similar image. So we would have some input noise from a latent space. So we can think of this actually as the encoder part, which we discussed in connection with variational autoencoders. And we just label this with an H, which is our latent space. And again, the idea is that this latent space is normally smaller than the full data set space, which we have. And the idea is also that we can model the probability of this latent space with some simple functions. So again, we are coming back to this topic of tractability and flexibility, which we mentioned in the very beginning of this lecture. So we want something which can be generated. So this feeds in, this function here, or this data set, feeds into a new differentiable function. And we simply call this function for G. And this function here generates some sample. So this is the generated sample. Which we call for G of H. And this again is then compared with what the discriminator, so the discriminator can actually take this as an input. So discriminator. And what we are doing then, so let's just put this one on the side here. So we have D tries this function D of G of H to be either to be 0, and what we also have is that G, this function G, tries this D of G of H to be equal to 1. So in simple words, what you could say now is that when we have denoted this generator and its output, so the output from the generator is given by this G of H here. The aim now is that the space which we have, this H, the dim of H, is smaller or equal to the dim of the original space. So in a certain sense, what we are doing now is something which is similar to the compression or the encoding in a traditional autoencoder. So we are encoding real-world information into a lower dimensional space. So the generator trains to generate samples which are good enough in a way to fool the discriminator, while the discriminator tries to properly classify real training samples versus fake, which are the output from the generator. Thus, this kind of game of adversaries uses a generator model G, which then tries to make this D G of H close to 0, or as close to 1 as possible, and the discriminator is incentivized to make this dg of h as close to 0, where 1 denotes real and 0 denotes fake samples. So the generative adversarial network that achieves equilibrium when the generator starts to easily fool the discriminator. So that is, discriminator reaches its saddle point. In theory, GANs have several advantages of other methods in this type of generative models, and they have their own set of problems, obviously. But these are discussed in more details in the textbooks of Rashka and also Goodfellow and other. But the thing is that in this specific case, what we need now is to define an underlying function which now defines this latent space and produces the input to the discriminator, and similarly the input to this differentiable function G, which we have here. Now, the way we train these networks is then as a game of two adversaries, and the generator is learning to generate good enough fake samples, while the discriminator is working hard to discriminate between real and fake. So more formally, if we now go back to the slides, so let's do that. Pictorially, this is what we are trying to achieve. So we have a discriminator which is trying to distinguish between real and fake data. And what we have then are these functions which we now defined in terms of a G. And here I should have changed my notation to H because I'm using H for the latent space. And the functions which we optimize is actually given. So in the training, we're actually optimizing this function which you see here. So we have an expectation value given by the probability of the data, which is given by this function d of x. And we have a function here, which is now based on the model, which then is trying to optimize the log of 1 minus d of x. This is the standard objective function, which is used in the training of a generative adversarial network. So the main motivation for the design of GAN is that the learning process requires neither approximate, like we had with the variational autoencoders, nor approximations of a partition function, which we again used, if you think back in the discussions of both restricted Boltzmann machines and variational autoencoders. So if we now are going to look at a way to perform these optimizations, let's now take a closer look at the program example. So in the beginning, when you start training the generator, you often just have what's called a uniform distribution, which defines just some kind of noise, which is then fed into this generator function. And then through this optimization process, we are then trying to get something which allows us in a discriminator here to distinguish between real and fake results. Now, in the slides here, there is an example of a program which I borrowed from the textbook by Rashka. And I invite you to take a look at chapter 17 in their case. The image here gives you a kind of overview of how the training is done. But let's take a look at the code here. So this code contains two networks, and these are just the standard feed-forward neural networks. And these feed-forward neural networks contain then a standard leaky Rayleigh function. It has a given number of hidden nodes, and it contains just one hidden layer with 100 nodes here. There is a input here, which is in the generator, where we could typically have something like 20 nodes in the generator. So that's the latent space. That reconstructs through the hidden layer here, and then fed into the a fully connected layer again here. We then can reproduce an image, and again this example here is tailored to the MNIST data set, and this data set has images of 28 times 28 pixels, and what it's trying to do is actually to regenerate this image here in collaboration with the discriminator. So the discriminator takes as input the images and then reshapes them, and then has a network which is actually the opposite of what we had. And then it tries through the sigmoid here to produce a final probability, which is either 1 or 0. So this discriminator receives the input from the data set, X, but it receives also this X tilde, which you see here. And then it is reshaping the data. There's a fully connected neural networks. We're using the leaky Rayleigh that just as a activation function. And then through the sigmoid, it produces either 1 or 0. So if we're looking at the code, there are some specific elements. There are two helper functions which are defined in the code here. So let's just run through this one in the meantime. Oops, I need to, okay. So I need to import PyTorch. Let me just do one thing and restart it, because I started it from a window where I didn't set it up properly. So let me just do that and restart it. Just a moment. This is my bad. Okay, so let's restart it. I actually started the Jupyter Notebook from a window, which was not included here. Now, GANs, this is a good question, actually. GANs are actually unsupervised methods. So let's just go back here and take a closer look at the code. And as I said, this is a code which I have borrowed from the textbook by Rashka and collaborators. And this is also a textbook which where you can access all the codes from their GitHub repository. And this is essentially a code which I took from that GitHub repository. So when we are setting up the generative adversarial network here, there are actually two functions here, one for each network, and that instantiates a model from the PyTorch neural network class, which is this one, and it's a sequential one. And this is the first part of the code, so that's a generator network and a discriminator network. And in this specific case, we have first the number of hidden layers is 1, the hidden units is 100, and then we have the output units, which is then going to be the image which we want to produce. So this is the input size, so that is the latent space, 20, and this is normally started by using, let's say, a Gaussian, or you could use a uniform distribution. So in the beginning, it would just be given by some kind of noise-like distribution, like a Gaussian. And then the discriminator set does the reverse, and you can see now again, it's a sequential neural network. It contains a given same number of hidden layers, the same number of hidden units, and then there's only one output unit, which is then given by the sigmoid function, because we want to decide whether it's a 1 or 0. So the next thing, so this one let's just run through this. The next one just prints the model and tells you what are the features of the discriminator and what are the features of so the first one is a generator model, and the second one is just a discriminator model. And then when we are training the data set, we are using the MNIST data set, and I hope this doesn't sound too boring. We've been using this data set again and again and again. And as you may remember, when you look at the MNIST data set, it contains 28 times 28 pixels. There is no color code. There's only one color code because these are grayscale images. And what you would need further is to specify the size of the input vectors to be 20, which is the vector which we have from the latent space, from the encoder part or the generator part. And since we're implementing a very simple GAN model for this specific case, then we are using fully connected layers, and we have only one hidden layer. So in this case, in this code part here, we're just initializing the network here. And you can see the different sizes here of the final size of the image which we are doing. Then when we are going to train the set, in defining that one, we are going to load the data set from the MNIST repository from PyTorch. So remember that all these kind of libraries, they have their own links to these different data sets. Yeah, but so you could assume that the data set is supervised, but what you are doing at the end is actually to obtaining a probability distribution which you can use to generate new images. So the code here, actually what we are doing now is to rescale the data as well. So this is, again, as I said, taken from the textbook by Rashka. So we the quantities which you will see here deal both with the rescaling of the data. So in principle, these pixels are images which will be in the range of -1 to 1, no, sorry, 0 to 255, and you want to scale them into a domain from -1 to 1. So it's pretty standard when you now look at the input data, reading in the data, is also to scale the data properly. So let's just run through this, defining the training set and reading in the training set. And when you're training the model, we are going to use this binary cross entropy as a loss function in order to train the model. And then we are going to set up the number of batches. There's going to be a probability for a fake result. And then there's going to be a probability for the real result. And for the discriminator loss, we have then two terms actually. So the loss for detecting the fake examples, which involves a probability for the fake example from the using the sigmoid, and then the loss for detecting the real example based on a real probability, which are then baked into the examples which you see here. And the ground truth labels for the fake term will be a vector of zeros that we can generate via a function which is called torch zeros. And then similarly, you can generate the ground truth values for the real image via a function which is called torch.ones. So all these functions here are actually doing these things and prepare everything for the training of the model. And this is going to take a little bit time here. And then when you're done with that, you can actually visualize the results. And then you can calculate the scores at the end here. So let's just wait a little bit with that. This is a simple setup because now it's running in the background. But what I wanted to say a little bit while this is running and we are waiting for the final results, I wanted to say a little bit about the diffusion model basics, which will be the topic for the lecture next week. So when we deal with diffusion models, they are actually inspired by non-equilibrium thermodynamics. And these models are extremely interesting. And in a way, they are superseding the basic philosophy of generative adversarial networks and also variational autoencoders and Boltzmann machines and so on. And I will try to motivate why. And then next week, we will dive a little bit more into the mathematics of the diffusion models. So they typically define a Markov chain or diffusion steps to slowly and add random noise to data and then learn to reverse the diffusion process to construct desired data examples. So if we now look at historically what we have been doing, the path which has been used is to look at probabilistic models. And as we said, they have two conflicting objectives. One is tractability and the other one is flexibilities. So models which are tractable, they can be analytically evaluated and easily fit to data like a Gaussian. However, these models are unable to describe data which are very rich and complex. And models which are flexible, they can actually be tailored to fit the structure and arbitrary data. However, if you now call back the discussions we had about Boltzmann machines, we need to deal with the normalization constant. And we need also to have a model for this phi here, so which gives us this flexible distribution. So computing the normalization constant is normally intractable. So what do diffusion models actually promise? They promise actually extreme flexibility in model structure, exact sampling, it sounds too good to be true, easy multiplication with other distributions in order to compute a posterior, and the model likelihood and the probability of the individual states can be cheaply evaluated. So this sounds like a dream come true when you now go back to the discussions which we had about the variational autoencoders. And the original idea is actually to use Markov chains to gradually convert one distribution into another. And this is an idea which was borrowed from non-equilibrium statistical physics and sequential Monte Carlo samplings. And these are something which we will discuss next week in more detail. So these diffusion models, they build a generative Markov chain, which converts a simple known distribution into a target data distribution using a diffusion process. Rather than using this Markov chain to approximately evaluate a model, which has been otherwise defined, one can explicitly define the probabilistic model as an endpoint of a Markov chain. So diffusion learning in this kind of framework involves estimating small perturbations to a diffusion process. And estimating small, analytically tractable perturbations is more tractable than explicitly describing the full distribution with a single, non-analytically renormalizable potential function. So just try to keep this kind of overarching picture. So what we are doing now, compared to variational autoencoders and Boltzmann machines, is that we, in Boltzmann machines and variational autoencoders, we're actually dealing with a full intractable and often non-analytically normalizable potential function or partition function and probability distribution. Whereas here, we are using the process of diffusion to estimate small tractable perturbations, which then allow us to describe the full distribution with single which actually allows us to describe the distribution in these terms of these single steps. So next week, we are going to look at the mathematics of the diffusion models and see whether these kind of features which we mentioned here are actually fulfilled. So diffusion models are actually the kind of dominating models among generative models nowadays. And we are going to use the last lecture to actually cover some of those properties. Now, this code is still running here, so it's soon done. I think I had some, was it 60? I think I had 60 epochs. I don't remember exactly. Yeah, I need to, I've always placed the GANs models as in the box of generative models, which are given by unsupervised, because you can, when I think of unsupervised, I actually think of unlabeled data. Yeah. Okay, this is still running here. So let's just wait a little bit more before we can generate data. And the final plot here is actually given by a comparison between the loss for the generator function and the discriminator loss, and then a comparison between the fake data and the real data. So I do think that we should soon be there. I'll need to remind myself of how many epochs we had. I think we have 100 epochs here. So this is still going to run a little bit, but we should have time for some questions here. Yeah, when I said as it's in the chat here, when I placed the GANs the way we've been treating them here as unsupervised, simply because we're not dealing with labeled data. But as Nikolai says here, you can actually be trained unsupervised, supervised, and semi-supervised fashion. So these are good questions. So we should soon be here, and then we can look at the difference between the different trainings. Sometimes it runs much. So actually training a generative adversarial network is often quite time consuming, which means that you would typically run these codes on a high performance computing facility, and you would run them on machines with many GPUs. So the University of Oslo has these machine learning nodes, which you can use. So you can get an account on them, and that should allow you to run with GPUs as well. And we are soon here now. So we should now be able to find a nice visualization and compare the results from the generator and the results from the discriminator. And what we're going to see then is that during the early stages of the training, the discriminator was actually able to quickly learn to distinguish quite accurately between the real and fake examples. And in the beginning, the generator is going to not resemble the data well. So let's now look at, it should be done now. So let's visualize the data here. So you can see now, as a function of the number of epochs or iterations here, you can see the different loss functions. And in this particular case, you see now that the discriminator is able to actually discriminate rather quickly between fake and real examples. And as the training proceeds, the generator will become better at the synthesizing realistic images, which results in probabilities of both real and fake samples, which are close to 0.5. You can look at the qualities of the outputs of the generator, that is the kind of synthesized images, and how they change during training. So if we then plot the images as a function of the training, you can see now that these images are not perfect, but as you keep training here, the images are getting better and better. And you can, after 100 epochs, you should be roughly able to classify which numbers these are. And I would say this should be number 0, and then we have this should be number 9, 6, and we have 2 9s here. So as you can see from this figure, the generator network actually produced more and more realistic images as the training progressed. And however, even after 100 epochs, the produced images still look very different from the handwritten numbers which you have from the MNIST data set. So you have to put in quite some goodwill here to actually say that these are good representatives of those numbers which we just discussed now. But you see now that the generator is the one which allows you to generate new data. So these are actually the images which are produced by the generator. And the discriminator is the one which now tries to discriminate whether these are fake or real images. So in this kind of competition between the generator and the discriminator, you're then able to implicitly extract a way to generate new images. It means, however, that you don't have, as you would have in a variational autoencoder, or if you look at a restricted Boltzmann machine where you have an explicit probability distribution, now you generate new images by an implicit usage of a distribution. And that's the main difference between, if we now go back to what we had on the whiteboard, if we now go back to the original scheme which we set up in the very beginning. So what we have is, in principle, a set of methods where we can either set up explicitly a probability distributions like we did with a restricted Boltzmann machine or a variational autoencoder. So the end product then is actually a probability distribution whose mathematical form, if you think of a Boltzmann machine, we do actually have. If you then go to generative adversarial networks, we avoid all these problems of approximating the probability, of setting up the normalization constant and to optimize that. But we then have the price which we pay is that the probability distribution is inferred only implicitly from the generator network. But it allows us to generate new images. And that's the big difference between discriminative methods and generative methods, in the sense that generative methods are, in a certain sense, what we actually want or we would prefer, because with generative methods, in particular, if we have an explicit PDF, what we can do then is to produce new events. We can test causality. What is the probability of A given B? With a probability distribution, we can estimate uncertainties and errors. And we can also use that to make predictions like we did with a standard feed-forward neural network and find correlations in the data sets. Now, with an implicit PDF, this is something which is more difficult, but it allows us, however, to generate, let's say, new images or generate new music And generative adversarial networks are extremely flexible. And I invite you to take a look at actually several textbooks on the market where generative adversarial networks, which focus only on GANs, and use them to, as we discussed earlier, to generate new images, to generate music, to generate the way your face ages with time, which is something which is very popular because you don't, for many companies, you don't need to take pictures of employees all the time when you have to update your access cards, for instance, etc., etc. So generative adversarial methods are extremely flexible and are widely popular. So we are going to end our discussion of generative models with a discussion of diffusion models next week. As we also discussed, these generative methods, they can be used on both labeled data and unlabeled data, but they're often used on unlabeled data. And that's why we often think of them as unsupervised methods, but they, like GANs, they can also be used on labeled data and semi-supervised methods as well. Okay, I'm going to stop here.